Hi, welcome again to the CSDS Cybersecurity Seminar at the University of Idaho. Jim Elsfoss here, Director of the Center. Today I wanted to talk about some common vulnerabilities you see and talking specifically about unsafe string and buffer functions and integer problems we see in coding. These are some of the most common types of vulnerabilities you do see in software problems in the internet. Now, the bigger list you can see of vulnerabilities exist. There's common, I apologize. There are several top vulnerability lists out there on the internet that you can look at. The SANS organization maintains their top 25 software errors. Open Source Web Application Consortium has web-specific vulnerabilities. There's the Common Vulnerability and Exposure Database maintained by MITRE along with the Common Weakness Enumeration. Both of these two at MITRE maintain information about vulnerabilities we've seen in the wild. Applications that have vulnerabilities get reported to this organization. They classify them based on the common weakness or the common vulnerabilities, document that information and put it out there so that others can learn from it. They tell you what the vulnerability was, how it occurred, and how you can fix it. And then there's also common attack pattern enumeration and classification also at MITRE. And so MITRE is sponsored to maintain a lot of these databases of information. It's a great resource to look at and learn about where these vulnerabilities occur in your code. If we want to look at different errors and look at these vulnerabilities, we see that there's a common categorization that can be used. And we can categorize them in one of three ways. Insecure interaction between components of your system, risky resource management, or porous defenses. And a lot of these vulnerabilities that are seen out there in the wild can be broken up into these components. One of these, which is fits under the category of risky resource management, is unsafe string and buffer functions. Okay, so what is buffer overflow? When you think about it in a piece of code, first you have data buffers that maintain information about your product, about the data you're processing, about the users you're interacting with, the other systems you're interacting with. From a software programming point of view, it's an array. It's a struct. It's an area of memory that's been mallocked. It's somewhere in the heap. Okay, it's on the stack. These buffers all have well-defined sizes when they are allocated, when they're created. An array of 100 elements has room for 100 elements. If it's 100 integers in a 32-bit integer machine, then that's 100 32-bit units, or each 32-bit unit being 4 bytes, it's 400 bytes long. If it's 100 characters, which are each 1 byte, it's only 100 characters, 100 bytes long, not 400 bytes long. If you try to write 500 bytes to one of these buffers, you're going to get an overflow. And the question is, what happens when you overflow the buffer? When you write too much information? Well, it's like overflowing a sink or a tub. The water goes somewhere. The data goes somewhere. Most systems don't stop you from overwriting the buffer. Now, when you're allocating memory in a machine, you're allocating variables. If it's on the heap, you're randomly allocating, dynamically allocating them. If it's a local variable, it's on the stack. Other variables that are allocated in the same way are adjacent to the array you have allocated. And when you overflow your array, you flow into those buffers. I'll actually draw this quickly on the board. The third place that you see this is when you have a program running. Every time you make a function call, you push data onto the stack. That data on the stack has the parameters, some special pointers. But one of the important things it has in here is the return address of where you came from. Stacks grow down in typical programming languages from high memory down. Every time you push something on the stack pointer decrements, goes down in memory. When you call a function, stuff from the previous called function, these parameters, return address, and all is pushed on the stack, and then space is allocated here for your local variables, which could include that buffer. If you overwrite the buffer, it overwrites up in memory and overwrites that return address. This is the most classic form of a buffer overflow attack, where you can basically overwrite the return address, doing basically a runtime patch of the code as it's executing. The common approach for doing this is you overwrite this return address and the parameters. When the executing code wants to return, it goes to this return address, which is actually treated as an entry point, or is the address of a well-known entry point into a library routine, an operating system routine, runtime routine, with these parameters that you overwrote on the stack. And so you can tell the system what to do. Call this function with these parameters. And that function could be anything as executing a shell script under new permissions, opening a library of network routines. Could do a lot of different things. Other types of attacks will actually have this return address just jumping to the code that you overwrote it with. And so you patch in the code. The slammer worm did this. It was a 400-byte attack. It overwrote a buffer and jumped to itself and then executed the code in there. And all in 400 bytes of data that just had overwritten a buffer because somebody didn't check, because they assumed the user would give them the right amount of data. There's no reason to give us that many, more than 100 bytes of data. That's why I allocate a buffer for it. If data is user data, then the user is able to put their data into your program. And if they do it beyond that buffer, they're able to modify your program. Other attacks we've seen is on the adjacent variables. It's a security control parameter. It says, hey, is this person authorized to do this? You change it from no to yes. Or it's an allocation of name of a file that they're supposed to access, or a password or other things, and you overwrite it. So we can return a lot of things, and that's the problem with this. How does it occur? How does it happen? People use, number one, unsafe library string functions. They get data from the user. It's a string of data, and they say, let's copy that user data from the input buffer from the network into my code. Let's use string copy. How does string copy work? How does the string copy function work? Standard library function in C. You've probably all used it. Well, those of you who've written C code. How does it work? It works by, you have a source buffer and a destination buffer. I'm going to write this one down because I love this one. So you have a source buffer and you have a destination address, and it says copy the byte from here to here and keep going until you find, I shouldn't put it, byte 0, which means end of string. If this source buffer is really long, a whole bunch of characters, and this is short, it'll overwrite this buffer. I have seen, I was investigating this earlier this year, 4 different implementations of the string copy library. The worst one I saw, the one I love the most, this is cryptic C, is while, let's see, star source plus plus, destination, excuse me. Star destination plus plus equals star source plus plus, semicolon. It says, I've got a pointer to a character, get its value, increment the pointer by 1, copy that value to this location, increment this pointer by 1. The result of this is the value that was copied, and the while says, if that, well, that's not a 0, do the copy. 1 line of cryptic code. I've seen a version on a 64-bit library routine was about 100 lines of code for source copy, where it checks to see if you're copying 64-bit values or single characters, so it can optimize and copy all 64 bits at once, all 8 characters at a time, and does really complex stuff. But almost none of them check, is the destination big enough? Because they don't know if anything about the destination. But there are library routines out there and functions, and we'll go back to the slides, that have these. The strcopy _s is supposed to be a safe version of this. You specify in your library call the actual sizes of the buffers. And we have a list of these here. And this can be memcopy too. It doesn't have to be string copy. String concatenate, scanf, reading. That's actually where a lot of this problems come. You're saying scan, read the user input and store it into a buffer, but don't limit how much the user can put in. And there are similar functions and similar libraries. Now, these are safer libraries. They're not safe libraries because you could be wrong about the size of the buffer still. If you tell it the buffer has 50 characters and only has 25, it'll stop you at 50. It'll stop you, but too late. And we've seen vulnerabilities about that. One vulnerability occurred where in one header file it specified a defined fixed size value for the buffer. In another header file it had a different size buffer. When they were compiling and testing the code, it used one header file. The production version used the other. Excuse me. The version that allocated the buffer used one of the default values. The one that tested the size used the other because the headers were included in different orders in different pieces of the code. And the compiler did not catch this at all. Compilers will miss a lot of this. There are ways of doing this. There are options in some compilers to say, don't allow buffer overflows. Check. Add code that every time I'm copying to a buffer, it checks the size. It's slower. It's much slower. But it's more efficient. Java does it built in. C# does it built in. It is possible. So a more precise example, here is we have a character, last name 20 we ask. Says enter your last name, then scans in the string to last name. If the user enters too long of a last name beyond 20 characters, it overflows that buffer. And this was CWE, Common Weakness Enumeration 120. Is the one on the MITRE. So if you enter like very, very long last name, which is 24 characters, you get a buffer overflow. And guess what? Bad guys can lie. They can tell you a different last name than their real last name. Another problem we have is with integers. Do we really know how integers work in our code? So here, I have an unsigned integer a equals 10. An integer max equals -1. If max is less than a, print the value, one is less than the other, I say max is less than a. Right? Else print max, or a is less than max, and prints out the order. I run this, and the output is 10 is less than -1. It says -1 is not less than max in the execution of the code. Why? Because in the C language, unsigned integers are given higher precedence or higher priority in the hierarchy than signed integers. So if you're comparing a signed integer with an unsigned integer, you convert implicitly the signed integer to unsigned. A negative value, that means the most significant bit is a 1, just becomes a very, very large number. And this very, very large number is not less than 10. And we've seen this in checks. When somebody's trying to check a buffer length, and they use length, a standard length is an unsigned integer, but then they compare it to an integer. And somebody may say, oh, it's a bad value, I'm going to give you a -1 to say there's no length. Common type of error or response you get from a library, and you combine the two, and all of a sudden you get an integer overflow. Probably some of the most misunderstood code out there is dealing with integer problems and integer conversion problems. And you got to know what's going on out there and think about it. So those are two of the common ones. I just wanted people to think about those. Now what I want to do is I want to talk about some mitigations, common practices you can do to deal with things like the buffer overflow, like the integer overflow, like some of the other types of security vulnerabilities you can see out there in the real world. These are best practice type of things. It's a start. It's not a panacea. It's not a silver bullet, but it's a start to what you can do. From the MITRE organization, CWE, there's a list of 9 of these, what they call monster mitigations. I've added a 10th one. The first 5 are their general mitigations, the next 4 or 5 are general ones. And we'll go over each of these in more detail. Number 1, establish and maintain control over all of your inputs. Improper input validation is number 1 killer of code. Like I've said before, you wouldn't pick up a piece of gum off the ground and just start chewing on it. Why do you take input from you don't know where and start just using it? That makes no sense. You should have a standard input validation mechanism that you always use, validate inputs for at least length, the type of the input. If I'm expecting it to be a number, make sure it's a number. If I'm expecting it to be a word, make sure it's a word. Checking the syntax, is it correct? Is it the proper format? One of the common problems we have is that somebody will insert extra characters in there to cause a misinterpretation of the code. Look for missing or extra inputs. Consistency across all the related fields, especially if the fields are tied to each other. You have a character and maybe a length specifier, a string and a length specifier. Are they related correctly? And your business rules, what are expected of these inputs? Check. Have validation rules that follow this. One of the good things to do is to use stringent whitelists as your best practice. If there's a well-set collection of values you expect, just handle those. Everything else would be considered bad. And do not accept invalid inputs, or maybe convert the invalid inputs to valid inputs. But don't ever trust what is coming across to you over the wire. I got a phone call this weekend. Somebody with a very strong Indian accent claiming to be from Microsoft technical support calling me about my Windows computer. And that there was a vulnerability on it, but they will fix it if I would give them my user ID and password. I did not trust this. Actually, I yelled at the guy. Somebody comes up to me on the street and offers me $1 million if I would just write them a check for $5,000. No. I'm not going to trust that. But if it comes across the internet, I trust it? No. I don't even know who's on the other side of that line on the internet. Why do I trust them? Why should I trust that they're doing the right thing just because they're using my software? Anybody who knocks on my door isn't necessarily somebody I want in my house. Okay? Understand the sources of the bad input. It could be standard user input. It could come from a network. It could come from a web form that was delivered to you. It could come from sources that are inside your code. If you don't truly know where that input came from, don't trust it. Validate it. Spend a little more time on your code. So monster mitigation, number 1. Number 2, establish and maintain control over your outputs. This is the often ignored dual of the input of validation. Attackers may actually modify your outputs. They may provide you data, information that changes your output as it goes to another system. And this is the root of most injection attacks. Cross-site scripting attacks and others. SQL injection attacks, you say enter your name, I give you name plus some code. And you send that off to the database query engine, including my name plus the code, and the database query engine treats it as code, thinking that you had done the proper validation on your inputs or your outputs, and you hadn't. Cross-site scripting, a user types in something into a blog or a comment, and they include web coding in there. And suddenly now you get pop-up screens and menus on the browser that's displaying because you allowed them to output code. And the recipient doesn't know that wasn't you. It came from you. It must have been validated by you. It must be correct. If possible, you should use structured mechanism and force separation between data and code, which would include all the quoting, escaping, encoding, and validation to say, hey, this was the data that I want displayed on this web page, and here's my control code to how to display it. and make sure they're separate, instead of just shipping it across and have the browser interpret it incorrectly. Oh, you said it was data, but there's code there, I'll run the code. That's your responsibility. You're sending it to someone else. You're sending them dirty data. You're like the person spreading those internet virus warnings. I don't know, the spam emails that don't say the right thing, that say, warning, don't turn on your cell phone when you're in the bathroom, it'll explode, I haven't seen that one, but I've seen some interesting ones, Okay. Understand the context in which the output's going to be used. Really understand that context and make sure you're giving the output that's expected of the other side, because otherwise you've got these improper interaction between components. They're expecting something from you, and it might be code you've written or somebody else has written, and you've done the wrong thing. Lock down your environment. Accidents happen. Be prepared by using defense in depth. Reduce your exposure. Your code that you're running on your system may make a mistake. Maybe your code, maybe somebody else's code. Why be vulnerable? Don't run as a privileged user, run as unprivileged. If you can download software onto your machine and install it without typing in a password, without doing anything special, you're in privileged mode. You should not be able to install software or do special things on your normal operating mode. You should be running as a regular user, an administrator only with password protections and password capabilities. Otherwise, any software you're running is running as a privileged user because you are privileged and you said run the software. And the system trusts that you know what you're doing and trusts that every piece of software you're running on the system is behaving the way you want it to. That doesn't sound right, does it? Disable verbose error messages for errors shown to users because you could disclose too much. One of the CVE warnings, CVE 2008-2049, basically a POP3 server revealed a password in an error message. Gave a little too much diagnostic information. Oh, you're entering the wrong authentication information. Here's the password you should have used. That's bad. I've seen other ones where they say, this is a problem. Here's the copy of the script code that was running that caused the vulnerability. Oh, and you look at it and say, oh, that's where it's checking for my password. This is where it's checking for authentication. Now if I do this, I'm correct. Here's the machine it was running on. Oh, now I know what machine to attack. When you're developing code, use trustworthy third-party libraries, not just anything you downloaded on the internet. Make sure it's well vetted, comes from a reputable source. It may still have vulnerabilities, may still have problems, but much better than that library, John Smith's CodeEmporium.com provided to you. Because guess what? I'll say this again and again. Bad guys lie. He may develop a really good library that has extra features in it just for him. And you've downloaded and you're using it. And maybe you're downloading it and using it in your product and giving it to your customers. Build or compile with security options. A lot of compilers actually have ways of doing security options, things like preventing buffer overflows or detecting the integer vulnerabilities. Now, not all of them work completely, but it's a start. Use operating system and hardware security features. Quotas. How long should this run? How much disk space can it be able to use? How much memory can it use? How many CPU cycles can it use? The protections are in the operating system. Use it. Limit it. And memory protection. Use virtualization, software jails, sandboxes, other techniques to say, run this application in a restricted, protected mode, so if something goes wrong, the rest of the system isn't compromised. Do this when you're doing software development, especially if you're doing complex software development, but any type. If I'm running something, I prefer to do development in a virtual machine. If I trash it, I'm trashing the virtual machine and not my whole development machine. Adopt secure configurations using security benchmarks or hardening guides that exist out there. There's a NIST standard and some other standards out there on how to develop this. Use the standards. People spend a lot of time researching better ways of making your code secure. Build on that. Use vulnerability scanners. Apply and to test your code. There's ones out there that'll test your web pages, ones out there that'll test your code. They're not perfect, but they help. Use them. Apply security patches regularly to your underlying operating environment. Your code may be perfect, but if your operating system isn't and somebody gets into your operating system and then infects your code, you're now shipping infected code. You wrote it perfectly, it got infected with a virus. Not your fault, but you shipped it. Mitigation 4, assume external components can be subverted, and your code can be read by anyone. If it's out of your sight, it's out of your control. Assume your code, your program that you're running, is operating in a hostile environment. It's behind enemy lines. It will be analyzed. It will be examined. They will reverse engineer your code. They will look at your code and figure out what it's doing. Don't try and hide it and think, I hid it in my code, nobody will find it. Security by obscurity means vulnerability surety. Okay, I'm not sure if that works well, but if you say, nobody knows because I've hidden it, they're going to find it, and then it's not hidden. The only thing that are good for security by obscurity is like your passwords. Passwords are good, and cryptographic keys, you keep those hidden. They maintain security because the whole algorithm is public, but still can't be broken. Hiding the password in your code to give you direct access to the system, no, they'll find that. Now, what if you have a client-server system? Don't trust the client to perform the security checks for you, even if you wrote it yourself. I have the client on my machine. I have complete control of the client. I can modify it. I can see what it does and emulate it and not even run it. It looks like it's your client. It's really me pretending to be your client. How do you know? You don't know. Do you trust it to say, I'm authorized? Sure, because I said so because you wrote the code? No. It may not be your code. Don't trust it. Have the authentication there. Number 5, use industry-accepted security features instead of inventing your own. It is much harder to do than you think to do your own security features. Especially, this applies to cryptography, authentication, randomness, generating really good random values, session management, logging, and other features. You should investigate which algorithms available to you are the strongest for cryptography, authentication, authorization, and use them. And use well-vetted standards. Go to NIST. There's the NSA Suite B that NIST talks about for cryptography. It's all based on elliptic curve cryptography as the vetted standard you should be using. They've vetted and approved certain libraries that implement these standards correctly. That's what you should be using. Don't invent your own crypto. It doesn't work. And just because you use more bits doesn't make it any more secure. I mean, I did consulting for a company that had a 32,000-bit crypto key. But the way they implemented it, I could break it 1 byte at a time, 256 possible values at a time. I broke that thing so fast. But it was a big number. It didn't matter. That's what computers are for, processing big things. And use the security features correctly. Use languages, libraries, and frameworks that'll make it easier to use the features and easier to put in a new feature if the one you're using is found to be not so secure anymore. Don't cut corners. Researcher, I think it was at Georgia Tech, did an investigation of Java apps that used secure access to websites, so used SSH or SSL connections to a website, but never checked if the security certificate coming back from the website was valid. It just says, I'm going to follow the standard, but I'm not going to do it. Half of the Java applets they found skipped that step because it was resource intensive. I don't need to check if the website I'm talking to is really the website it claims to be. I'm doing it securely. I'm talking to this thief securely, so I'm good. Nobody else can hear what I'm saying to this thief. Think about it. Don't cut corners. All right, general stuff. Use libraries and frameworks that make it easier to avoid introducing weaknesses. New ones have come out, especially recently, that it makes secure implementations much easier. The safe string handling stuff. Parameterized query mechanisms, such as for SQL, where SQL you say, here are the parameters, the username, the stuff that comes from the user, and it protects it all, wraps it separately from your code. or input validation schemes that are out there that'll do the right validation for you. Integrate security into the entire software development lifecycle. This type of discussion I'm giving now, the top 25 lists, vulnerability scanners are just the start. You need to build in security from the beginning. And every software development company should have a software security group. And I don't mean two guys for a company with 20,000 employees, because they got to work with those 20,000 employees. Look at industry. There's industry efforts out there such as BSIM, SafeCode, OpenSAM that are secure architecture, secure coding, best practices for industry. They're a good thing to follow. Should use a broad mix of methods to comprehensively find and prevent weaknesses. There's no silver bullet out there. You need to use automated static code analysis scanners that check for potential buffer overflows and integer problems, and manual static code analysis. Walkthroughs. Have somebody else look at your code. Have a standard way of looking through the code to see if it does what it's supposed to do. And then automatic dynamic code analysis, like fuzz testing. Fuzz testing is a good way of stress testing your code. It tries wide ranges of inputs. Invalid inputs and sees if your code breaks or not and handling the invalid inputs. Manual dynamic code testing. Run the code, but do penetration analysis. Try certain combinations of things. Do threat modeling. What are the concerns? Now, threat modeling has to be legitimate. Threat modeling can't be, nobody's going to hack me because they don't know about me. That's not a good threat model. Application firewalls and external controls in your development environment. Have things protecting your software that's not inside your software. Education and training in the development environment, keeping abreast of what the latest problems and solutions are. Standard coding standards within the development environment. One, it helps with the walkthroughs, everybody can read your code better. Two, it avoids some standard problems. There's some really good coding standards out there that if you follow, avoid some misinterpretations of how the code works and makes it less likely you'll have vulnerabilities in your code. And then there's the software security framework part of BSIM, the SFS, which has some additional ideas in there that are really good. Allow locked down clients to interact with your software. This is one I love. If the user locked down their client, that's a good thing. Don't shut them out. Offer them at least limited access. Just like don't forget about iPhone access. You develop a web page, but you can't read it from an iPhone. You're locking out part of your customer base. That iPhone may not have the same security or operabilities as your Windows. Think about it. People can make choices in the browsers like, do I want to store cookies? Do I want to run or execute JavaScript? Do I want to have allow browser plugins to execute? In my development environment, I may turn all that off. Or a sensitive production environment, I may turn all that off, and then suddenly I can't use your website. I can't use your product because you think I have to have this newest, greatest thing that you built. The thing that drives me crazy right now is Flash. Every website I'm going to wants to use Flash. Flash, it's having problems with Firefox browser. It keeps halting, breaking. It's had some other problems. I don't want to have to use it. And there's websites that are disabled because I don't run that plugin. Why? Don't force me to run software I don't want to run on my machine. That's your fault, not mine. If I want to block things down on my machine, let me. Think about it. Think about allowing me to be safe. Not just because it's the latest, greatest, whizzy, prettiest interface you can use. Bad guys lie. Last thing. Your code is behind enemy lines. Everyone could be a spy. Someone is trying to subvert your system, steal your intellectual property, your customer data, personally identifiable information. They want to use your resources or damage your system. And they don't need to know who you are or where you are to attack you. They can randomly attack your machine having no clue who you are and not caring. Viruses come out there, spam comes out there, they don't care who they hit. If they send out 100 million spams, 1% responses to that is 1 million people. 1/1000th of 1% is still 1,000 responses. That's a good day for them. If they can get 1,000 people to buy a product, in one day for sending out 1 million emails that didn't cost them much of anything to send out, they're doing well. If they've infected a website and you visit the website, you're the one visiting the website. They're not doing anything. They've set it up, and if it can infect your machine, all the better for them. Understand, it's dangerous out there, so be safe and have your code operate safe. And I'm going to stop at that one. So, thank you.